everybody. I'm Seth. Today I'm going to talk to you guys about how we built stream synchronization in service of watch parties. First off, this was a collaboration with Ginger. She built a lot of the player UI you're going to see in a bit and lots more stuff. So thank you, Ginger. I'm going to give just a quick overview of what I think a watch party is and like why people want them. Then I'm going to do a demo. I'll talk through some of the challenges that we faced when we built this whole thing out. And I'll sort of motivate that with some data that shows the challenges, shows how we overcame them. And I'll end with a quick discussion of how we think all of this scales. Does this work? No. Yes. So what is a watch party? I think of it as 2 or more people enjoying the same piece of content at the same time and sharing in the experience. So take 2 people, put them in different rooms, make them watch Naked and Afraid. Don't let them talk to each other. That is not a watch party. But if you put them in the same room, take out their headphones, and make them watch Naked and Afraid, now it's a watch party. So the cliche is that this happens most frequently on like Puppy Bowl Sunday. Everybody gets together. They're like in the living room. They're eating nachos. They're eating kibble. And they're like talking about the ads, I guess, or something. So nowadays, though, I don't think it's necessarily limited to people in the same room together. So a coworker was telling me about his teenage daughters who regularly FaceTime their friends to watch shows together. So literally, they like call each other up on FaceTime. They're like, 1, 2, 3, play. And then they play. And then they're like, no, pause. And then they pause. And they make that work. So that's cool. I think also, another phenomena that a lot of us are familiar with is a significant other goes on a business trip. You're in the middle of binging your favorite shows on Philo. And you have to like coordinate exactly when you're going to watch the next episode to hold the relationship together. So also a watch party. A last use case that we're particularly interested in is the idea that talent can watch a show alongside the audience. So it'd be really cool to watch SpongeBob with Obama, but it would also be cool to watch Storage Wars with Ivy the King Calvin. Those are kind of the use cases that we had in mind. How do we build something that will support those use cases? So first and foremost, the content needs to be synchronized. So if you're in the watch party, you need to be seeing the same content at the same time as everybody else. Seems kind of obvious. It sort of already works this way for live TV, right? We've heard like a lot of talks about low latency to live and making live TV work this way. I think that what we're really talking about when we talk about low latency to live is not so much like getting users as close to the live edge as possible, but synchronizing users with the people at the event. So it's, I think, really, live playback is a watch party. But we want this to work beyond live. So we want it to work for VOD. We want you to be able to scrub back in live and rewatch the instant replay and bring your friends with you. So if you're doing that, that means the player controls need to be shared. And if the player controls are shared, then it needs to be easy to switch between synchronized and unsynchronized because, if I want to go back and watch some really gruesome part of The Walking Dead, I don't necessarily want to have to take everybody with me when I do that. Cool. So that's what we think makes a watch party. Now, I'm going to attempt to show you a demo. Here we go. Before I go into this, I just want to say that this was a Hack Week project. It's not yet live in production. If you go to philo.com, and probably you all have Philo accounts, but if you go to philo.com and make an account for the very first time, you will not get the feature flag. You won't see any of this. If you're interested in trying it, I'll put my Twitter stuff up after. You can DM me. I'll give you the feature flag. You can try it out. So with that, and a nod to the gods of live demos, here we go. So I've got 2 users logged in here. By the way, the South Park audio glitch was me testing this earlier, so I apologize. So I've got 1 user logged in over here, Now I can go over here. I'm just going to refresh this because Lord knows. This is a different user represented by the whale. The user over there is going to be represented by a drumstick. There's the drumstick. I'm going to play this. We are now enjoying a watch party together. Now, while this loads up, I'm going to give a little quick spoiler, which is that our algorithm doesn't converge immediately. So these will not appear perfectly in sync right away. You can kind of see that. I can adjust the window a little bit so that you can really see it. Yeah, this is not great. It takes about 15 seconds to converge, which when you're up here talking to people is a really, really long time. But eventually, these will converge to within about 500 milliseconds of one another. The controls are shared. So if I pause over here, it's paused. If I play, hey, it plays. I can scrub back, and it scrubs back, and hopefully plays again. And then I can unsync and control everything thusly. So here, I'm going to leave the party now. Bye-bye. And I can now scrub normally, and the party proceeds. So that's what we built. Let me talk about some of the challenges now. I guess I should stop the video. Remember, I left the party. OK. Cool. So the challenges. Everybody needs the same content, first and foremost. So that sounds really easy. That's like what we do as media streaming companies. We give everybody access to the same content. Except we do server-side ad insertion, so it's not 100% straightforward. So I'll talk about that a little bit. Once everybody has the same content, we need to tell the players where to go. So the player needs to know where it should be at any given time. And once the player knows where it should be at any time, we need to compensate for the fact that it might take one player a different amount of time to get there from another player because there are variable network conditions across players. So first off, everybody needs the same content. That really means that we have a shared video timeline of some sort. We chose to reuse our existing HLS and DASH streams as our shared timeline. Quick note, it was really tempting to go down the route of building out some new RTP-based solution for this, but it would have required a lot of rework, right? We have to build basically everything downstream from the transcoder from scratch, including the control plane across all, 10 different players that we have. So that would have been a lot of work. Trying to implement RTSP in BrightScript doesn't sound very fun to me. The nice thing about using our HLS and DASH timeline is that our manifest generator sort of already supports an idea of a playback session that can be shared. So when you go in, generate a manifest, inside of a new playback session, we can spit out HLS dash, lots of other different metadata against that one timeline. So we can generate, all kinds of different manifests against, one timeline with one set of stitched ads, importantly. And the last really nice thing about reusing our existing streams is that we don't have to write a bunch of new player code. So ABR is hard, analytics are hard. We have crazy ad markers on our scrubber. We have all kinds of insane seek restriction rules. We don't have to re-implement any of that across our many different platforms. We can just use what we have. Cool, so now we have our shared timeline. How do we tell our players where to go? This is the most naive solution imaginable. We have a server, and it broadcasts a message out to all of our clients that says, go to position 0. And the clients are going to go to position 0. Here is some code. That's what this might look like. I'm going to build on this, I promise. It sends a message down to all the clients. It's like, here's the reference position. This is where you should go. pretty obvious problem here that it doesn't account for latency between the client and the server. So one client receives this message at t equals 1 millisecond, and another receives it at t equals 5 milliseconds, and those clients are going to be, or sorry, t equals 5 seconds. Those clients are now 5 seconds out of sync, and our watch party is like ruined. So we can use UTC time to solve our problem. If we assume that all of our clients have synchronized clocks, then we can piggyback on top of that synchronized clock to synchronize the playback. Now, we heard from Will yesterday that that's not a great assumption to make. Like, if we don't do anything, if we just say, oh, everybody's using NTP, it's totally fine, that's not going to work. So we send a server time down, we compare it to local clock, and make adjustments accordingly. But the overriding assumption here is we are able to get to synchronized UTC clocks on the client. So now instead of saying be at position 0 at time equals, or sorry, say be at position 0, we say be at position 0 at time equals 1 o'clock. If the client receives the message after 1 o'clock, which they probably will, they can do a simple calculation to figure out where they should be at the current time. So our synchronizer structure from before becomes this. We added a reference time. So now we have a reference time in UTC, and we have a reference position, and we can calculate our target position as now minus the reference time plus the reference position, and we're in great shape. Except, how do we pause? Because time, for better or worse, keeps moving forward as the Earth spins around the sun. So we can solve this by adding a play state to our data structure. If we're playing, then we calculate our target position as before. If we're paused, then we just pause at whatever the reference position was. So now we have our synchronizer pretty well defined. I mentioned that we have shared controls, so we need to allow our clients to mutate this thing. So that's a pretty simple operation. A client can say, hey, change the state to paused, and the server will broadcast a message out to all the clients that says, hey, here's the new synchronizer with its new state. Similar operation for seek, where instead of changing the play state, we're going to change the reference time, reference position to something else, and the same thing happens. Cool. So now we've told our players where they should be, but how do they get there? Well, we need to account for buffering time, right? We need to account for the time that it's going to take the players to download the video. So again, starting with the naive solution, client knows that it should be at position 30 at time 1:30. We're going to just calculate the target like we saw before, try seeking there. If we're able to buffer fast enough, then we play, where fast enough is within some threshold that we define. Otherwise, we go back up to 1 and keep trying. OK. Now I'm going to show some data. This is a very busy chart. We have UTC time going across the x-axis, and we have presentation time going across the y-axis. And we've defined a target position as a function of UTC time, and so it goes up linearly with UTC time. I mentioned that we're going to define some threshold. If our player position's within the threshold, then we're going to let it play. Otherwise, we're going to keep seeking. And here's what it'll look like, right? Yeah. We'll just seek somewhere, and then it'll play, and it's going to be right in line with the target. No. This is what it looks like. So what ends up happening is we seek somewhere, buffer. Buffering is the player position not moving forward, and UTC time moving forward. And then we're buffered. Yay, we can play. But we're way outside of our threshold. So we seek again, and we buffer and we seek, and we buffer and we seek, and we buffer and we seek. And now we have a Sisyphean player with no watch party. So we can add an estimated time to buffer to our algorithm from before. I think collectively, the people in this room could probably dream up like, I don't know, 1,000 different ways of estimating time to buffer. inputs from the ABR system and all different types of machine learning. We chose a really simple algorithm to start that looks at estimated weighted moving average of historical seeks. It works okay. I think there's some tweaking that we need to do. But this is what our chart from before becomes. So we have an initial buffer time estimate that we make before we have any data. In this case, this was a throttled connection. So our initial buffer time was wrong. So we buffer for a really long time, and then we're able to make a better guess. And then we play right into the target, well, within the threshold. So there's one important thing to note here, which is that we sacrificed content. We buffered enough video to play, and then we had to drop that video on the floor because we were outside our threshold, and we want to be in the party. So what that means in real terms is that we're increasing our startup latency with this approach. But we think it's worth it because it's fun to watch video with your friends. So another thing to point out here is that there was some estimation error. We didn't exactly hit the nail on the head, and we won't always. And there's different ways to approach these fine-tuned adjustments, but a really nice way to do it is to add playback rate into the mix. So we have our playback threshold, where if we're within the dotted lines that I showed before, we're going to let the video start playing, assuming that we've buffered. We can add a new threshold that we'll call the sync threshold, where it's a little finer than the playback threshold. If we're not within the sync threshold, we can adjust the playback rate up or down to get ourselves in line. So this is really nice because it helps with things like frame drops and drift, and you don't have to disrupt the user experience by doing a seek. You can just do these little tiny adjustments to the playback rate instead. So this is what that might look like. You can see it's a smaller diff. One note, I'm sorry to keep picking on Roku, but not every platform offers playback rate controls. Depending on the platform that you're trying to implement this on, depending on the player, you might have to just seek ahead really far and then pause for a while and wait for the target to catch up. But maybe if there's someone on the Roku team here, they can make a push for playback rate. All right, so last thing to talk about here is that seeking in this world that we've created for ourselves turns out to be really hard. Earlier I mentioned that we're going to mutate the synchronizer whenever we seek, and so the simplest way to do that is just we're going to set the reference position to the desired seek position. But given our time to buffer estimation that we just talked about, if we do the mutation that way, it means that the user is never going to see the desired seek position, right? So let me show you what that looks like. So say the user seeks here, and we set our reference position there. The point that we're actually going to move the player to is up here, because we know that it's going to take some amount of time to buffer. So that's not ideal. We can fix this fairly easily by flipping it on its head. And instead of moving the session, moving the party to the desired seek position, we can move everybody else back by the amount of time that we expect the initiator to buffer, right? So, here's what that looks like. Say that now the user seeks up here. We move everybody else back here. And by the time the user that clicked to seek has buffered enough video, the session will have essentially caught up to them. So that's pretty good, but it's not great, because if there's users with variable network conditions in the party, they're going to have different levels of experience. So for example, if the user that initiated the seek had a very fast connection, and everybody else had a very slow connection, the users on the slow connection would miss the point that the seeking user seeked to. And conversely, you might end up putting a bunch of users on a fast connection really far behind the seek point if the initiator had a very slow connection. But the alternative is to only allow playback once everybody has buffered enough video, which doesn't seem great. So And it won't scale, right? If we have like 1 million people in a watch party watching SpongeBob with Obama and one person has a terrible connection, then it's going to ruin it for everybody. So just recapping the trade-offs that we talked about. First off, we sacrifice content on the seeks. So that means more startup latency. Like we just talked about, with seek position, your mileage may vary depending on network conditions. And lastly, we're futzing with playback rate, which some users might find a little off-putting. Maybe we make it a preference someday. I don't know. So lastly, scale. What happens when Ellen decides to tweet out a link to a Philo watch party in the middle of the Puppy Bowl? Assuming Twitter can stay up with all the traffic, I think we'd be in pretty good shape. So I sort of skipped over how we implemented this all on the server side, but most of it's pretty lightweight. We're only sending messages down to clients on state changes, so seek, pause, play, basically. There's an exception to that, which is, if you noticed in the demo, there was a little stack that showed all the users that are synced up in the session. We track that. We track it with heartbeats that clients send when they go into or out of sync. And if everybody goes out of sync at the same time and then is like trying to sync back up, maybe there's an upstream issue in our video pipeline. Everyone's buffering and like constantly going in and out of sync. That could be pretty heavy duty. We can solve it by just only showing you synced players for your friends or a subset of the synced players that we think you'll care about. But overall, we think it'll scale pretty well. So that's it. I'll just say again, this was a Hack Week project. We have a lot more work to do on this. We have a lot of other really interesting problems at Philo. Come join us. My DMs are open. You can DM me your reactions to this, or if you just want to talk, I'm around. So thank you.